Hello everyone, and welcome to today's webinar. I'm McVicker. I'm the product director at Gamlen, and I will be talking today about using USP 1062 data to better understand compaction. The United States Pharmacopoeia published chapter 1062 a couple of years ago. It's on tablet compression characterization. And essentially, it tells you how to analyze compaction. So first of all, why do we want to analyze compaction? All of us, we all want to make better tablets. And a good tablet is something that's strong enough to withstand handling and processing. So something that's not going to cause low hardness problems or any kinds of breakage or chipping, friability problems. But we also want our tablets to be porous. They need to be porous enough so that they're not hindering dissolution. We need dissolution to happen within a reasonable time frame. But something that's very porous will not be very strong, and vice versa. So there's always a trade-off happening there to try and make the best tablet. We also want our tablets to be free of defects, and defects such as capping and lamination, which is associated with very low levels of porosity in a tablet. And we don't want to see sticking and picking in our tablets. And this is caused when the blend isn't appropriately lubricated or sufficiently lubricated. The problem with this is that if a blend is very lubricated, then the particles won't adhere to each other, and then you have weak tablets. So again, you're working with a trade-off. And these are the things that make developing a good tablet formulation and tablet manufacture challenging. And ideally, we would like to know if we're going to avoid all of these problems before we enter full-scale manufacture. And this is where compaction analysis comes in. If you're not carrying out compaction analysis, then it's likely that you're trying to infer compaction from other powder properties. If, for example, you are looking to use a new supplier of an excipient, or you're changing the source of an API, it's likely that you'll look at samples of the current and the potential new one and look at various physical properties, say particle size, shape, surface area, possibly solid state form and density, and try and see what the differences between the powders are, and try and estimate whether those differences are big enough to impact the quality of the final tablet. This is similar to the approach you might take if you are troubleshooting an issue in manufacture and you expect that a material is at fault. If you had a formulation that was working well and now you're seeing an issue and you suspect it's a particular material problem, you would look at good and bad batches of this material, you would look at its different physical properties, and again, you'd be trying to see where the differences are, and are these differences significant enough to impact tablet quality. The problem with this approach is even when you know the history of the formulation, you understand it well, when you understand the material and its function, and when you understand how all these properties could potentially impact tablet quality, and you understand how they're all measured, even with all that information, you're only ever making a best estimate. You're saying that from this, it's likely or unlikely that this difference between these powders is going to impact tablet quality. Whereas if you move away from inferring compaction and start measuring it directly, you can give much more definite answers to these questions. And this is the area I worked in previous roles as a materials scientist. I worked on tablet formulations, and when I moved to measuring compaction directly, I was able to give my colleagues much more definite answers on whether the changes they were considering, for example, may cause the tablets to become weaker. And this is instead of saying it probably will or probably won't. So this makes a big difference. So USP 1062, this was published in order to try and give guidance on how you should be analyzing compaction and how you should be characterizing compaction. And the quote here essentially says that we have been making tablets for over 100 years, and we are still seeing the same problems we always have. We're still having capping and lamination issues, low tablet hardness issues, and so on. In fact, we have a book here in our office that was published in 1906 that describes the same problems. So this chapter was published with guidance on how we can finally overcome these issues in tableting. And what they recommend is that you generate the data described by the compaction triangle. And you can see the compaction triangle, each of the three corners is a different value, and each side of the triangle is the relationship between these values. In order to generate this data, you would need to make tablets at a known compression pressure. Then you would measure their mass and dimensions to get their solid fraction, and then you would break them to measure their tensile strength. When we're looking at making tablets, we measure compression force, but in order to generate this compaction triangle data, you need to convert force to pressure. And in this way, you take account of the tablet's dimensions. Similarly, you measure the hardness of the tablet, but you need to convert this to tensile strength to take account of the tablet's dimensions. And these are fairly straightforward calculations, but these mean that the tablets that you analyze in your compaction analysis don't have to be the same size and shape as those that you're making on production. You can still get valuable data using different size and shape tablets. And the third corner of the compaction triangle is solid fraction. If you're not familiar with the term solid fraction, it's often useful to think about it as the inverse of porosity. So a tablet is made up of pores and solid, and the solid fraction is how much of the tablet is solid. The one piece of information you need to have about your material before you carry out compaction analysis is you need to know the true density of the material you're studying. This, for most well-known APIs and excipients, if they've been well studied, then you'll likely be able to simply look up the true density values. If you are working with a blend, the true density value is an additive value. So if you know the composition of your blend, how much the true density of each component and how much is in it, you can calculate the true density value. But if you don't know it, you can use helium pycnometry to measure it. But in many cases, if you are simply measuring or doing a comparison within a set of samples that are all the same type of material, then you could use an estimate. You only really need a more accurate value when you start comparing different materials. So that is the compaction triangle, and you can see there's three relationships between each of those values: compressibility, compactability, and tabletability. I will say for anybody that isn't a native English speaker that if you look up the dictionary definitions of these names, there is no discernible difference between them. These have arbitrarily been assigned by the USP chapter to mean these relationships. So how do you go about this? How do you analyze compaction? It's 3 steps. You need to make some tablets, you need to measure their dimensions and mass, and you need to break them. If you are using our equipment, I would generally recommend making 15 tablets. You would use 5 different forces to make 3 tablets at each force. So now you have a profile for each relationship in our compaction triangle instead of a single point. Typically, you can do this with less than 2 grams of material, and you could do a whole test in about half an hour. When you've done that, this is the type of data you'll then be looking at. This is some tabletability data. So this is how the tablet tensile strength changes with compaction pressure. And I would say tabletability is the most useful section of the compaction triangle. Whether you are looking at optimizing a formulation, or whether you're comparing, say, different samples of the same excipient, say from different sources, or any kind of investigation, the tabletability will give profile will give you useful information on how strong your tablets are. This gives you a way to assess and compare, say, different formulations or different samples to see which will give you the strongest tablets. And it's important to recognize that not only are the absolute values of this useful, but also the shape of this, these profiles are also useful. We tend to think that you increase the compaction pressure and you expect to have an increase in tablet strength as a result. But this only is true up to a point for most materials. Most materials at some point will start to plateau, where you get no improvement in strength with increasing compaction, or you may even find a drop-off point where increasing the compaction pressure will actually create weaker tablets when overcompression starts to happen. In the example here, there are 3 formulations. This was a set of client samples. They were starting with formulation A and they made a change in each case for formulation B and C. It's a pretty dramatic example, but you can see the change in formulation C made the tablets a lot weaker. And as I said, tabletability is very much the most useful piece of information from the compaction triangle. The next relationship is compressibility. And this is how the solid fraction of the tablets change with compaction pressure. Here, if you are studying samples of the same material, you say, again, different sources of an excipient or an API, then you won't see significant differences here. If the composition of the samples is the same, then there shouldn't be significant differences in solid fraction. So, but it is useful in generating or building a formulation. The solid fraction, as I said, tells you how much, what level of porosity is in your tablet. This is why most companies will put in a limit at which they won't work above, say, a solid fraction of 0.9, because there's too few pores to be sure for reasonable dissolution time, and capping is more likely at high solid fractions. You can see here that the change that was made between formulation A and C, that you can see there's a significant difference in solid fraction for formulation C compared to the other two. So this would indicate that I would say that's a compositional change. The one exception I would say when it comes to comparing different materials from, or the same materials from different sources, where solid fraction does become useful, it was an incident where I was comparing samples of a material from 2 different supplier sites, and I saw a significant difference in solid fraction, and it turned out that the supplier was actually, one supplier was providing us with a different solid state form than the other, and that's the only time you should see a significant difference between materials that are the same, if there's actual difference in solid state form. Otherwise, it only indicates a difference in composition. The third relationship is compactability. In the previous 2, we were changing the compaction pressure and seeing what the result was. Here, we're looking at how tablet strength changes with solid fraction. And this is interesting because you can see formulation C, several of those tablets have the same solid fraction as formulations A and B, but the tablets are still weaker. So these tablets have the same number of pores as the tablets in A and B, but they are still weaker. This indicates that the reason that those tablets are weaker is not simply due to the level of pores present in the tablet. There's something else happening that is making the tablet, because of the material is being intrinsically weaker and not just a different level of pores. So again, this is useful in building up a formulation. And those are the three relationships that we see in the compaction triangle. Moving away for a moment from what is described in 1062, I mentioned at the beginning that we also need to consider lubrication when we're analyzing compaction. If we don't, we're likely to end up with sticking and picking problems. But 1062 doesn't provide any advice on how to evaluate lubrication. You can evaluate it by measuring the detachment and ejection forces. And these are the forces you need to get a tablet out of the die. When you've made a tablet, the tablet is stuck to the base of the die and the walls of the die. The detachment force is the force it takes to detach the tablet from the base of the die, and the ejection force is the force that it takes to push it out of the die. So obviously, if this is easier, the forces are lower, and the blend is better lubricated. So I'm going to show you some examples of compaction analysis data. Here, I'm focusing on a comparison of different lubricants. When you're looking at lubrication, the two main things you're interested in is how the lubricant is affecting the tablet strength and actually how well it is actually lubricating the blend. The top line of graphs are the tabletability profiles, which are how the tablet strength varies with compaction pressure, and the bottom row are the ejection stress profiles. So these are the assessment of how well the lubricant is actually lubricating the blend. The first two graphs on the left show lactose lubricated with 1% magnesium stearate and 1% sodium stearyl fumarate. The magnesium points are in black, and you can see from the top graph that the magnesium stearate tablets are definitely stronger than the SSF tablets across all the compaction pressures included in the study. So the magnesium stearate gives us stronger tablets. If you look at the lower graph for the ejection stress, you can see there's not a huge difference in the ejection stress values. You could argue that the magnesium stearate is very slightly lower ejection stress values. So here, the magnesium stearate is giving us stronger tablets, and it's the slightly better lubricant. So all things being equal in this situation, you would choose the magnesium stearate over the SSF. The middle two graphs is the same test carried out with Ludipress, which is a pre-blended excipient. And here again, we're using magnesium stearate and sodium stearyl fumarate. If you look at the top graph, you can see that the SSF tablets are stronger across most of the compaction pressures. But what's interesting is that you can see this sudden drop off in tablet strength at about a compaction pressure of 300 megapascals. This is particularly interesting because this is the overcompaction that I mentioned earlier, that when you hit some materials too hard, you actually reduce the strength of the tablets. And although you might say that if you were happy that you were only making tablets at these lower compression pressures, you're not concerned about this, you might be happy with the SSF, but the magnesium stearate is the much safer option in this case. You can also see from the ejection stress profile that the magnesium stearate tablets give you lower ejection stress tablets, so it's the better lubricant. So again, in this situation, you would go for the magnesium stearate. Interestingly, when you do the same study with mannitol, there is no significant difference between the two lubricants. So in this case, you could simply choose which is more cheaper or more readily available. You could, of course, do this study with different amounts of lubricant and different blending times to fully optimize the lubrication. But this is just showing you how quickly and easily you can make these choices with compaction and with compaction data. Similarly, this is a comparison of different sources of MCC. If you were choosing a source of MCC for a formulation, again, I'm only looking at the strength of the tablets and the ejection stress profile. You can see that source A of MCC gives you weaker tablets, but the tablets are actually slightly better lubricated because they have lower ejection stress values. So depending on your concerns for that formulation, you might choose you might decide that it's more important that you have as strong a tablet as possible, or more important that it's better lubricated. So this is an easy way to choose which source of MCC is right for you. Finally, I mentioned the risk of overcompaction earlier and the different shapes of the tabletability profile you can get. You can see on the left, there's 3 different types of behavior. You have type 1, where the tablet strength keeps increasing with compaction pressure, although less and less as the pressure increases. Type 2, where you now have overcompaction happening, where the strength of the tablet is actually dropping off at higher compaction pressures. And this is very important to know if that's your material when you go into production, because often when you get low tablet hardness values in production, an operator may choose to up the compaction pressure, and then you could end up with even weaker tablets than you started out. And the final type is where you see an increase up to a point and then it plateaus, which is common with most materials. So that is the end of the presentation. It was a whistle-stop tour of compaction analysis and 1062, but if you would like to find out more, please visit us at our booth or visit our website at gamlentableting.com. And we are actually also interested in expanding our distribution network at the moment. So if you are interested in working with us, please contact us. Thank you very much for listening.
Thank you so much, Rebecca.